but even if it's not yours and you like it, just take it. Otherwise, it's gonna land in a bigger box, and in 2 or 3 years, it's gonna be just dumped. Well, so a quick review. This picture represents a visualization of a standing wave. These colors, red, blue, have nothing to do to actual color of actual light we may see. This is a color-coded picture, that's it. And it helps to visualize what might happen everywhere at the same time. And the result that happens is because when two waves interfere, we may have two extreme situations. One has a name. Destructive interference. So two pulses travel towards each other. We should imagine they travel on the same row in this model. And the pink line represents the actual sum of two pulses. So they, in this situation, try to kill each other. Yeah. And the case we consider when waves are coherent, have the same frequency, same magnitude, same wavelength, everything is the same. In this situation, there is a moment when they just disappear. Individual waves would have been up or down, but when they overlap together, superposition is happening. That's it. Momentarily, there is nothing left. And another situation we call a constructive interference, when both waves move in phase with each other, so they try to enlarge the total displacement. And this situation or that situation happens at different locations, but at the same time. And we just need, again, to keep in mind that when here and now two waves cancel each other out, there is nothing there, never. Yeah? It's zero. Actual individual waves would change in time. So this grows, and this grows in opposite direction. So they always cancel each other out. At the location of a minimum of intensity, we will see nothing, never. This is a slightly different situation, because here what is happening, they grow, and then they decrease, then they change the direction, grow in opposite direction, decrease. So this arrow represents the maximum amplitude at the location of the maximum intensity, but technically in time it changes. But if it changes very, very fast, our eye, if it's light, just doesn't see that instant, which takes a fraction of a second when there is nothing, instantly. In our model, we could see it because the model is slow. Yeah? The model is slow. So right here, see, black and red and blue and black, etc., etc. So that's what is happening with the total wave. It oscillates. But imagine we make it travel, move faster and faster and faster. In that case, our eye just registers some average intensity, which again, the color of what we see depends on the light we will use. If we use a red light, we're going to see red maxima. If we use blue light, we're going to see blue maxima. If we use green light, we're going to see green maxima. And to figure out what will be happening at specific location, we have two conditions. This is the condition for the minimum of intensity. And I've mentioned briefly. So this has been derived, but what does odd mean mathematically? In mathematics, any odd number can be represented in this form. And if we change this variable m, 1, 2, 3, 4, 5, this set of whole numbers gives the set of all odd numbers. Yeah. 2 times 1 minus 1, 1. 2 times 2 minus 2, 3. 2 times 3 minus 1, 5. So this is how we write it mathematically, and of course we just simplify it. 2 divided by 2, 1 divided by 2, and that's what we call a mathematical condition for a minimum of intensity. And this is a physical representation. This is the mathematical representation of the same fact, no intensity happening there. This is more convenient because m lets us count those minima. We will call them first, second, third, fourth, fifth, etc., etc. And the same we can do for maxima. The condition for a maximum looks simpler. We just need to be able to fit a natural number, a whole number of wavelengths. Where to fit it? In path length difference. That's it. And this is the summary. What should we keep in mind? Well, a whole number, yeah, which we use to count things. People use a letter M or N or even K. Doesn't matter what letter we use for counting things. We need to remember what it represents. And it represents slightly different things. For maxima, we start counting from 0. For minima, we start counting from 1. That's a little difference. Another thing, for the length of the path, again, people use different variables. Lowercase l, capital L, R, X. It doesn't matter. We need to just know what it represents. So this is, again, how people describe a set of all odd numbers. Sometimes people use a plus. It's a matter of personal preference. We use a minus here. Why? Because I like it. If you don't like it, you can use a plus. But in that case, you would have to start counting differently from a different number. Well, oops, go away. So we can always figure out what is happening in whole space if we know how to figure out what is happening just between the sources. So if we look inside, we know right between this coherence in phase sources, in the middle we should have the maximum of intensity, an antinode of a standing wave. And now this line, this point represents the whole line with the same condition. And if we move a quarter of a wavelength to the left or to the right, we reach the minimum of intensity, the node of this wave. And that will represent the whole line of nodes with the same path length difference, etc., etc. So please tell me what you think about this particular point. One wave travels a longer distance, second wave travels a shorter distance. They overlap, and well, we know what should be happening there, maximum of intensity. So what do you think should be path length difference equal to? We have different ways to approach this question. And by the way, your pictures from yesterday are posted on Blackboard, so you can check them. And some are very good, very accurate, but it's actually handy to browse through pictures and see what other people did wrong. And some people made some mistakes, like a wrong type of a lens, or using a mirror instead of a lens, or using wrong rays, or just being not very accurate, shaking hand. That's what I call it. And yes, if the picture is not very accurate, that might lead to a mistake. So here, please choose your answer. Why is it number 3? Did we have an answer? No, we didn't. Okay. Let be number 3. Yes. So please enter your answer to this question into the 3rd slot. So the question number 2 was asked, answered, 100% correct answers. I'm happy. Let's hope that next question is number 4. Well, so again, we have different ways to approach this situation. Number 1, we can just count this number. Well, first, every time when we talk about a minimum or a maximum, we can use an equation, but we have to use a correct equation. We have to choose an equation which corresponds to, well, what's happening. In this situation, this is supposed to be the maximum. Okay, green is good. The maximum, how do I know? Well, it lies on the line of maxima. And in my enlarged picture, so that will be central. That will be the first. That will be the second. So for the second maximum, the number n is supposed to be equal to 2. And there is a slide in the future with some terminology. We don't call the middle maximum like 0th maximum. We call it the central, because it's at the center of the picture in the middle. And the first to the central we call the first. The second to the central we call the second. That's it. Now, of course, we could have repeat the same reasoning we've done yesterday very briefly. We know that for all points which lie on this line, path length difference is the same. This is basically a definition of this line, path length difference. And this is supposed to be equal to literal difference. But to calculate this difference is easier to use that enlarged portion of the picture between the sources. So this is this maximum, and that what's supposed to be called L1. That was supposed to be called L2 for this particular representation of this maximum. And so there's another maximum number 1 and maximum number 2 on another side. And the picture says this distance should be equal to L2 as well. So technically what we're looking for is this, right? 1, 2, 3, 4, 5, 6, 8. That quarters. So it should be equal to 8 quarters, which gives again 2. So n equals 2. But if we just know how to point a finger and count first, second, third, we don't have to do this calculation every time. Any questions? So here again, I've used the fact that in a standing wave, well, in any wave, the distance from the crest to the equilibrium is a quarter of a wavelength. Well, so if we talk about sound waves, we can listen to the sound, and we did it yesterday. Now we talk about light waves, so we have to use the ability to see, our vision. And the only thing is, we know light is here, but we don't see it here. We only see it on the screen. To see it here, I need something to use as a screen and then look at it. I could have used a photocell, if you know what it is. It's a tiny cell which generates electricity when light shines on it. Come back. Willpower. Instead of an eye. So, and we could use that photocell, place it everywhere, and measure the intensity of voltage it generates. At the minimum, it will generate nothing. At the maximum voltage. But of course, the easiest way is using a screen and look at the screen. Now, first we need a dark, one thing to say. To make a stable standing wave, both sources must be coherent. Same phase, same amplitude, everything should be the same. Only the location of the source is different. That's easy to do for sound waves or for waves on water. But if we take any two bulbs, even if they look identical, they actually can't generate coherent light. Even if we take two laser pointers which look alike, still they will not be coherent. So this is the problem with light. We need two coherent sources, but we don't have them. So the approach is actually very simple. It took a while to figure it out, but the approach is simple. We need one source. We just have to split the light it generates into two individual sources. And now, so to do that, we use two slits. Well, we have to use very narrow slits, close to each other. But now, each slit like that start acting like an individual source. And behind this optical device, double slit, we should be able to see the interference pattern. The type of that pattern should look like this. So this is a handy applet. So let's say we have one slit. The wave traveling through, you can try it at home. You just need water in a pan. Left. That's basically an experiment I've done yesterday with water. And now we have two. And as long as wave starts overlap, we start observing maxima and minima. Constructive interference is happening, destructive. If that would have been a sound wave, we could walk inside and listening to the change in the loudness. For a light wave, we just have to place a screen here and look at the screen. And that's it. And what should we see? Well, if we use the green laser pointer, we should see green pattern. If we use a red laser pointer, we should see red pattern, etc., etc. Somewhere we should have nothing. That's what we call a minimum of intensity. But somewhere we should see something. Let's see. All we need is a laser pointer and 2 slits. Nowadays, to manufacture 2 slits, it takes practically no time. These things are very cheap, because what is a slit? It's basically a scratch, very thin, tiny scratch. So you have to just make 2 scratches. It's hard for us, people, to make 2 scratches like 3 micrometers away from each other, but we have devices which can do it very easily. So I just need to plug it in, point at the screen, and here we are. See? And of course, we can do it like this. So if I hold it like this, that means my slits are vertical, and the light now kind of behind the slits spread horizontally. I can move it like this. Doesn't really matter. Now my slits are horizontal, and the light is being spread vertically. And well, for double slit, it's not very visual, but we can try. The only thing is, never aim it in your or anybody else's eye, because laser pointer is a powerful light source. All right. Oh, here. See? Those light rays travel away, and they get wider and wider, spread from each other. And when they hit the screen, we can see the pattern. There are green dots with black things between, black spots. We call them fringes. And that's the standard double slit interference pattern. And of course, we can calculate the location of each black spot, or the location of each dark spot or fringe. We just have to apply those conditions combined with the geometry. What geometry is about? Well, there's a certain distance from the screen to the slits, and we always eventually end up with 1 or 2 or several right-angle triangles. And what do we know about right triangles? Everything. However, there is a very convenient difference between light and sound. A sound wave is larger. Light waves are very, very short. So, well, nano means 10 to the negative 9. So light waves millions times shorter than sound waves. So which means this distance from the, well, 2 sources, 2 slits, to the screen is billions of times longer than single wavelength. So we can use this approximation. We can use this fact for an approximation, which will be very convenient. So if I enlarge this picture, what would I see? Source, I call them sources. It's just easier, but we know that technically those are 2 different slits. Source number 1, source number 2. And there are 2 waves traveling away so far away that there is practically no angle between these lines. They are parallel. The angle which is important, is, so that's the screen. Eventually, they meet somewhere and generate a maximum. But right across the slit, well, first of all, we have to observe the central maximum with m equals 0. This is maximum with m equals, well, m. So this angle matters. It is related to this length. How would we calculate the path length difference? Well, basically, this is how much longer the first path relative to the second path. Again, it's only in our mind on the screen, this distance is about 10 centimeters. In reality, those are micrometers. So in reality, there is no spacing. They hit the screen at the same location. And how would we calculate this path length difference? Well, we see a triangle. Do we see a triangle? I do. This is a triangle. That's what we call a distance between the slits or saucers. And this will be the same angle. And path length difference over d should be equal to the sine of that angle. So the path length difference should be equal to d times the sine of that angle. What angle is this? Well, this is the angle at which we are observing the maximum number m, the mth maximum, which means this path length difference also supposed to be equal to, according to the condition for constructive interference, this product. That's it. This is the actual working condition for mth maximum, which we observe on the screen, which generated by two sources or two slits, coherent. Well, the picture, the condition. We could have done the similar reasoning for the minimum. Path length difference still equals d times sine theta, but for the minimum it should be equal to a different combination. For a double slit interference pattern or for a double source interference pattern, we have two conditions. That's not always the case, but here we have two conditions. One tells us how to find the location of a maximum on the screen. Second tells us how to find the location of a minimum. We don't have to use two, actually. We can use any if we want to. The summary. Another way of the summary with the picture. Again, this is the gross exaggeration, very, very gross, like billions of times exaggeration. In reality, they're very close to each other. And, well, that's the terminology part. If we talk about maxima, in Greek, single maximum, plural maxima. If we talk about maxima, we call them central, then first, then second, then third, and that corresponds to that number m we use in the equation. If we talk about minima, there is no central minimum. It doesn't exist because we always have a maximum in the middle. That's why we count from 1, and we call them first minimum, second minimum, third minimum. Of course, we have them on both sides. There's complete symmetry. Any questions? That's terminology part. Question. Number 4. Let's say we move the slits away from the screen, so we can do that, how would that affect the interference pattern? What would we see happening with those fringes? We only have three options: nothing, or they move away from each other. We say the pattern expands, or they move toward each other. We say the pattern shrinks. And you actually kind of saw it when I was moving back and forth. However, as we know very well, the picture worth, what is it worth? I would say 2,000 in physics. So we don't really have to draw two slits or two sources every time, but it's kind of handy. So let's do red ones, doesn't matter. There is a screen here. So we know what really happening. There is a light wave traveling toward this slit. That's an actual experiment. Well, there is a screen with two scratches, and after that, light waves travel toward the screen, but only along certain directions. For example, actually it travels behind this part of the screen, behind where normally we would observe shadow. But in reality, in this experiment, actually light does travel and reaches the screen. That's what we call the central maximum. Also travels toward the first maximum. This is theta 1. Of course, we have another one on another side. This is theta 1. Toward the second maximum. The number of maxima is fixed, it's finite. We're going to talk about it later. That's what we call theta 2. All angles are measured from the central line. Now we are moving the screen away or slits away. It's easier to move the screen away in the drawing. So now my screen has a new location here. So now this kind of disappears, doesn't prevent light from traveling anymore. So what's going to happen? These rays will travel further until they reach the new location, the new screen, not the old screen, but at the new location. That's it. And what should we see? What is happening to this distance, the distance between two adjacent fringes? Increases. So the picture, the pattern expands. And if we move it backwards, the pattern shrinks. So this distance between the slits and the screen affects the pattern. How? Well, if this distance increases, this distance between two fringes increases. Come back. I'm spending too much my energy today on unnecessary things. Any questions? I know what's happening. I sent a reminder today to IT about this situation. And they make me pay for that. moving on. So, just a note. What's the difference between an ideal imaginary case, if we would have used two actual coherent light sources? In that case, of course, from each source, light would be traveling equally in all directions, and the pattern would be bright, almost equally bright everywhere. In reality, since we use slits, the power distribution is different. So the pattern looks slightly differently, very bright in the middle, then kind of die out. If we want to measure the intensity, and we could have, and we will next week, if we measure the intensity of light using a photocell, if we move it back and forth, we will never see a picture like that, because we don't have sources, we have slits. So we would see a picture like this. Intensity, the maximum of intensity, then it dies out. And now we got to solve a problem. So red light, red light has a specific wavelength, but it has a range. This is one of examples. Is used in Jungs experiment. Thomas Young published the first paper on this material in 1801. So the double slit experiment has a name, Jungs experiment, and we know the spacing between the slits, how far the screen is. That's it. So of course we just have to draw a picture. The screen. Just want to make it just strictly vertical. It's easier. Now here we have two slits or two sources. We don't really need to see them. We know that right across it we will observe the central maximum. Let's make it equally long. So what else do we know? We know D equals 0.0001 meter. So 1.2 times 10 to the negative fourth. 0.12 micrometers or 120, 0.12 millimeters or 112 micrometers. And the distance from the screen to the slits equals 2.75. And find the distance between the central maximum of fringe and the third one. All right. So there is the first, there is the second, there is the third. On both sides, of course. That's the third one. The distance we are looking for is this. People would call it L3. Of course, we got to use a triangle. So a ray, light ray, which reaches the screen at the location of the third maximum, is bent away from the central line by the angle we call theta 3. So if we look at this triangle right now, we can write immediately that L3 over L is supposed to be equal to tangent. Oh, the third theta. That's geometry. Now we can use physics. That's the third maximum. First of all, it is a maximum. Second of all, it's the third. That's what we really need. We have already two. We call them Republicans and Democrats. We need the third. So we have to write a condition. We have to, but why would we write a condition for the minimum if we talk about maximum? How does it look like? Well, in general, this condition looks like this. That's because it's a maximum, and specifically because it's the third maximum. we can write it like this. Now, what else do we know? Well, we know the wavelength and we know the distance between the slits. So this will be equal to 3 times 664 nanometers divided by 0.00012. For you, now, it's time to take a calculator and calculate this number and then plug it in here and then calculate this number again. That will be equal to 2.75 times tangent of this angle. However, I'm not going to do that because I know a secret. It's been passed from a physicist to a physicist for generations. For a small angle measured in radians, there is practically no difference between values of sine of this angle, tangent of this angle, and the angle itself. So, this is what I need to do. This is a very good approximation. And since the sine and angle are also practically equal to each other, that will be equal to this. And now I can take a calculator and calculate it. There will be no difference how we do it, of course. It's just a kind of time-saving hint. That's it. So, and the answer is supposed to be 0.0456 meters, or about 4.5 centimeters. So, if you look at this calculation, you can see the angle is even less than 1 degree. And you saw that those rays were traveling away from each other slightly, but they still remain very, very close to each other. Those angles are very, very small. That's not always the case, but for a double slit or double source interference, that is practically always the case. For numbers up to like m equals 5 or 6, definitely works. Now we're going to talk about another type of interference. A single slit interference. So close this. Do this. This is a model of a very common experiment for waves generated on the surface of water. You can put some obstacle with the hole, and when waves travel through, they practically don't bend at all, keep traveling in the same direction. And there is practically no wave behind this. That's what we call shadow. But what's going to happen if we make the slit narrower and narrower? The bending about the edges will become more and more visible for a very small slit. And small means small enough. This size is very close to the size of the wavelength. In that case, we can see a very, very strong bending. And if we had placed a screen right here, we would start seeing some pattern. It wouldn't be just one bright spot. It would be bright spot, but also some regions, some spots, some fringes with no light at all. Then another bright. So there is an app you can play with to see at different single slit interference patterns. You can change the wavelength. Let's say, I don't know, red 560. No, that's red. 450. Oh, I'm getting shorter. I need longer. Blue, red will be like 750. Oh, yeah. Oh, that's a double slit. Oh, where is my single slit? Okay. If you want, we can find it. It's supposed to be somewhere here. There are many, many applications, handy applications here. Single slit. Okay. The same. So let's say 750. Red. A very, very, very bright spot in the middle, and then very narrow region, fringe with no light at all. And let's say 450. Similar situation, but the width of the bright spot in the middle is narrower. Well, actually, we can see it. You know what? There's one thing I forgot. It's important. So just 30 seconds. Did I tell you this room is awful? So I need to place my devices very far away, but you can't see it because it's very far away. So I need to transmit my picture to the computer. Come on. Oh, come on. Okay, it's working. So it's just going to take a minute because it's important for the lab. Right here, you can see two optical rails. And both provide the, oh, I can hear myself, red laser beams. One will be traveling through double slit, and second will be traveling through a single slit. So we will see the difference in the pattern, of course, on the screen. And first, of course, I need to turn it on. Okay, there's light here. There's light there. Now I need to aim it at the screen. And now, okay, I already see them, but light. Oh, what? Just mute it. So, two patterns, which is which? Well, we know that for a double slit or double source interference pattern, we should see several relatively narrow bright fringes. And have some relatively narrow dark space between those. So here, this one, I think this is central maximum, first, second, etc., etc. It dies out eventually, but still later come back. So here, what we have, very wide central maximum. Then there is a very narrow region with no light at all. Then we see another maximum, no light at all, another maximum, no light at all. The problem is these are very wide, so we cannot pinpoint a specific location of a bright region. So what do? Well, we can pinpoint a specific location of each minimum, first minimum, second minimum, third minimum, and that's what we should count. So for interference pattern of a single slit, we only can use minima. All right. So I don't need this anymore. Back to the show. Why it's still working? I can. Well, so that's demonstrate the difference between a wide slit. In that case, we don't see any interference happening, but if the slit is narrow enough, so narrow, that is, well, hundreds of sizes of wavelength maybe. In that case, we observe interference pattern generated by single slit. Now, what's happening? Well, even if it is narrow from our perspectives, it's still wide enough for a relatively large number of light waves traveling through. And what's happening? Well, that depends on the direction. This picture represents a specific direction from a horizontal, specific angle, when those waves cancel each other out. Why do we need this? Because we have to talk about minima, not maxima. How do they cancel? We see this is out of phase with this. So, and for each wave from below this point, there is a wave from above, which will cancel it out. So there are pairs of waves canceling each other out. And that's not the only possible angle. There's another angle like that and another. What do we see here is the path length difference between two extreme rays should be equal to exactly wavelength, or 2, or 3. In that case, light traveling in those directions actually will not be traveling at all. They will be canceling each other out right here in this region, and in this direction will be no light. And that's what the maximum means. So, of course, it's a triangle. That's the width of the slit. And if we use this triangle, this will be equal to hypotenuse times the sine. And a common point of the confusion is this equation looks like an equation for maximum. But for this particular optical device, a single slit, this equation represents location of minima. And there are no maxima. There is no location for maxima for a single slit interference pattern. Well, now, of course, all we need to do is just look at the summary. So we count minima, first minimum, second, nth. And now we have to solve a problem. Life with a given wavelength passes a single slit of a given width. We just have to draw a picture. So a single slit, a screen, a screen. So we should see a very, very bright spot right in the middle. This is the first minimum on one side, left or upside. This is the first, this is the first minimum on another side. What we're looking for is the width of the central maximum, and this is this. I know there's no standard letter. I don't want to use W. W is this, the width of the slit. Let's call it D, like a diameter or something. Well, what we know is that there is no light traveling in this direction, and there is no light traveling in that direction. So if we draw a line perpendicular to the screen, that will be theta 1, or that will be theta 1. And this, we can call it x, should be equal to exactly a half of what we're looking for. So basically that's what we need to do, 2 times x. How do we find x? What do we need to do? Well, we have a triangle. This distance is equal to 2 meters. So we have a very long right angle triangle, theta 1, well, L, x. So again, x will be equal to the distance between the slit and the screen times the tangent of this angle. And again, the angle is very small. You see that distance? Like, I don't know, 15 yards or meters. And the size of the spot was like 5-6 centimeters. So if you calculate the angle, it will be a very, very small angle, less than a degree. So we can use an approximation. So how do we get the angle? Well, we can write an expression for the mth minimum and use it here. For the first minimum. Again, I used an approximation. Sine of that angle will be equal to the angle if it's measured in radians. And now D will be equal to 2 times L times wavelength divided by the width. So that's going to be equal to 2 times 2 meters times 640 nanometers divided by 3 micrometers. All calculations are very straightforward. Any questions? I'm going to finish it later. Doesn't really matter at this point. Do you have a question? Okay. The last optical device to talk about today is a diffraction grating. A diffraction grating is a device which has lots of slits, many. So what do? We take a piece of glass and we make one scratch, second, third, fourth, And we keep scratching until we get like thousands or even more. What's going to happen to the light when it travels through diffraction grating? Well, first of all, we can use our imagination. So lots of light travels through. And those rays should interfere. By the way, the distance between two slits is very, very small. And we can imagine that we're actually covering, it's not easy to do, but easy to imagine, covering all the slits except two. Light still will be traveling, but not as much as before. So the pattern should be much, much, much dimmer, but still all maxima should be located at exactly the same places. So, which means we can use exactly the same equation for the maxima. But the picture now, because this distance is very, very small, the picture now is very wide. There's a maximum, another maximum, and vast space with no light at all. Don't believe? Let's see it. That's what we're supposed to see. So all I need is a diffraction grating, and if you look at it, you actually don't see any scratches, you don't see any slits. To us, it looks like a regular piece of glass. But if I shine, dead. If I shine a laser pointer at it, see? Light travels through and generates a pattern. There's a central maximum, the brightest one, and then there's the first on the left and the right, second on the left and the right, and vast space with no light at all. It's actually kind of handy. Look at it if we make it travel in a vertical direction. Well, we need something to scatter light so it would reach our eye. See? Of course, light travels, but only in a certain direction. And on the screen, it generates, it excites, makes bright fringes, bright spots. We call them maxima. The equation for each maximum for diffraction grating is the same as the equation for each maximum for a double slit situation. But there is only one equation we can use for a grating for maxima. Because minima don't exist. Again, the space with no light is so vast we cannot pinpoint a special location for that. Well, what do we do now? Of course, solve the problem. Light with a wavelength of a given, so that's a blue one, incident on diffraction grating with 100 grooves, lines, slits, those same names for the same thing, per millimeter, 1,000 actually. The screen is 2.75 meters away. Calculate blah, blah, blah. Everything. Yeah. So diffraction grating, how do we draw a diffraction grating? We don't. Yeah. Grating. Something. We just need to indicate the location of device, and we need to know what kind of a device is it. And there is a screen far away. So we always should see a central maximum right across it. And the first theta 1 on both sides, maybe the second, third, etc. The distance from the grating to the screen is 2.75. The wavelength equals 480 nanometers. And what else do we know? We also know that it has, well, that's density, something per length, that's density, 1,000 slits per 1 millimeter. That's what we know. That's not what we need. We need D, the distance between two adjacent slits. Why? Well, because we want to use this equation, which describes the locations of each maximum. So what do we do? That's it. Have to divide 1 millimeter per 1,000 slits. So that gives 10 to the negative 3 millimeters, or 10 to the negative 6 meters, 1 micrometer. Now, let's see what we need to calculate. Distance between the first and the second. Okay. There is a second right here, or here. This is our x. Now, we know that we can calculate this distance. We call it L1, the distance from the central maximum to the first one. We know we can calculate the distance from the central maximum to the second one. We call it L2. And if we look at the picture, distance which we need to calculate is just that. And that's what I want to say about it. I want to address a second question. How many bright spots, fringes, how many maxima would we see? Well, on the screen, we see central, first. Now we know it will be second. Question is, will we see the third or fourth? Well, how does angle change? The angle changes from 0 to theta 1 to theta 2. What's the maximum value of that angle possibly being achieved? Theta maximum, theoretically, is equal to. That's where physics intuition starts working. What number should I write here? Someone has to say something, you know, yes? Absolutely right. Thank you very much. Now we can move to the next step. It cannot be more than 90. If it's slightly less than 90, technically it should reach the screen somewhere. If it's more than 90, that light just travels away from the screen. So the theoretical maximum is 90 degrees. That theoretical maximum, which means actual angles might be less, or sometimes, which is impossible, but just in case, equal to 90. So what does it tell about the sign of this angle? What will be the limits? If the angle might change from 0 to 90, the sign of that angle might change from what to what? Absolutely. So, well, technically, which means this ratio might have only values between 0 and 1. For a fixed wavelength, for a fixed grating spacing, there is always maximum M, which allows this condition to be true. If we increase 1, 2, 3, 4, 5, eventually we get a number, so such number that this ratio will become greater than 1. So that number can't exist. So the last number which satisfies this condition is the last number for, well, represents the last maximum we can see. So there is maximum for M. We call it M maximum. It exists. Question. This, well, is a visible spectrum. It's a rainbow. Yeah, you've seen it many, many times before. We know that the frequency changes from low frequency for the red light, then it goes higher and higher and higher and higher. And I can use exactly the same diffraction grating I've used a couple of minutes, well, 5 minutes ago. But now, instead of using only one laser pointer, only green one, I will use two, green and red. And of course, on this screen, we will observe two interference patterns, one because of the red laser, second because of the green laser. So the question for you is, which pattern do you expect to see? Let's just see. Let's just see. So, well, red is a little bit dimmer. Okay. Where is it? Yeah, red is not very bright with this guy. Oops. Okay, that actually might be better. They alternate, but or bright. So the green, so where is the central maximum? Well, right here. When light doesn't travel through the grating, that spot shows the location of the central maximum. Now we make it travel through the grating, and we see the green is closer to the central, the red is farther away from. By the way, you know what? You don't have to use a laser pointer. Let's make a rainbow. So the closest to the central is green, then blue, then green, then yellow, then red. The central is white. Why? Well, because it's a combination of all. They all travel to the same central maximum. So that's why it is white. But the first maximum is colored. It's reached for different colors at different location. And of course, the answer is in the equation, which relates wavelength and angle. If we write that equation, so we have diffraction grating, we have a screen, maximum, d times sine theta m equals m times lambda. Well, we can just pick one m equals 1. So sine of theta equals wavelength over diffraction grating spacing. When wavelength increases, that should increase the angle. The red. So, well, and one more thing, of course, it is a wave. So when frequency increases, wavelength decreases. When frequency decreases, wavelength increases. So when we go from blue to red, frequency decreases, wavelength increases. That should increase the angle. So this is a summary, all possible patterns, and this is the summary, all possible equations for a single slit, diffraction grating, double slit, and that means we are done with this particular type of interference, which is good, because now I can start a different type of interference. Thin film interference. Any questions about anything? All right. What is a thin film? A thin film is a very, very thin film. What does it mean? It means you have to have something thick, put something very thin but transparent on the top of it, and have something thick and transparent on the top of that. That's what it means. And there are many technologies which actually use thin film interference. Coating, for example. If you have a piece of glass, if you're really, really into making good photographs, your camera has very specially coated lenses. Those lenses usually have a thin film which cuts out the red light. Well, because of what? Because of the interference happening inside the film. Please, what do you think? When a wave travels from one medium into another medium, what should happen to something? And you may not recognize this question, but that's basically a copy of one of your homework problem questions.
This is actually number 6.
How would I know it? You tell me. Let me check. It is 6? Okay, thank you. So, first of all, don't answer speed does not change because we know it does. This is a copy of a slide from before. When light travels from one medium into another, speed of the light changes, or speed of the sound changes. So basically you have to choose between frequency and wavelength. And what did you choose? Well, you have to choose something. It's a web-assigned question. You have to make a choice and enter it. You have to follow your gut, wherever it tells you. You have to enter it. Did you enter it? Yeah. You're wrong. The frequency of the property of a source, the wavelength is the property of a wave. The source must be presented to generate a wave. So there's something vibrating with a given frequency, and that frequency of vibration get transmitted through all possible media. It's just a push. They push on each other with the same frequency, equally fast, equally quickly. So the wavelength definitely does not change. The frequency definitely does not change, but the wavelength is supposed to be related to the property of the medium. How? Well, that's the wavelength here. For light, there is no difference between traveling in air or vacuum. So for light, air is like vacuum. It's very rare. It's not dense. For us, it makes difference between being in air and vacuum, right? So the index of refraction is equal to 1. The speed of light is equal to 3 times 10 to the 8th meters per second. Water. Index of refraction equals about 1.33. Speed of light will be equal to this. It moves slower. But the frequency here should be equal to the frequency there. And equations which relate speed, frequency, and wavelength should be the same. So we just have to make a statement about frequencies. This is this, which means this is this, which means speed of light in vacuum divided speed of light in the medium should be equal to wavelength in vacuum divided by the wavelength in the medium. But this ratio has a name, index of refraction. So it turns out the wavelength should change by the factor of n. For light traveling from vacuum into transparent medium, water, glass, anything, wavelength shrinks. That actually means, by the way, if you look at the same source in above water and in water, the coloring should change for you. Maybe not dramatically, but should. So that's the summary. That's the same summary with everything we know about light, including Snell's law, including critical angle, just in case. Now, we can start talking about phenomenon, and mathematics will be tomorrow. Today, we just look at what does it mean. That's what it means. This applet represents a phenomenon we call thin film interference. First of all, we have to imagine that in real life, of course, all these waves not located away from each other. It's exactly same wave traveling straight down. Well, that may be air, glass, water, or glass, diamond, air, wherever. It doesn't really matter. Any three transparent media, and this, that's what we call film. This medium should be very, very thin. It practically within several, or even less than several, one wavelength, or even part of a wavelength of light. And so an incident ray reaches this interface, and here we observe two phenomena. One we call reflection, second we call refraction. However, again, in the easiest situation, when light travels straight down perpendicularly to the surface, it doesn't bend. So there's no angle. What's happening here? Second boundary, second interface. Again, some part of the light travels through, some part of the light getting reflected. We don't care about this. It travels away. We only care about light traveling back because we are imagining ourselves looking down. So these two reflected rays might actually reach our eye, but they meet each other here, and when two waves overlap, the interference happening. And the superposition principle says we may have three options. Number one, we may have a constructive interference, amplification of brightness. Number two, we may have a destructive interference, no light at all, or something in between. Something in between is not interested. We ignore that. We only have to talk about two cases. When would constructive interference happen and bright light would be reflected up to our eye, or when would destructive interference happen and no light would be reflected, which would mean actually it all travels through. That when we use a film to actually amplify a certain color to travel through this device. Now, the most important thing to remember for the thin film interference is that everything is happening inside the film. Which means for all our calculations, no matter what we want to calculate, the wavelength in all equations should be in the film. That's what people sometimes forget. If you read a problem, it tells you a number for the wavelength, but that number almost always for the wavelength in the vacuum, and you cannot use that number. You have to use the number for the wavelength in the film. Well, that's a natural place to stop. Mathematics is very simple, actually. We're going to finish it tomorrow. And the hope is that by tomorrow, 9:29, you will be able to finish all homework 3 part 2. The lab is in 136, so if you do the lab today, 136, it's across the hallway, close to the entrance in the building.
Just wondering, I missed lab yesterday because I didn't feel very well. Can I pick it up today?